right, the recording has started.
All right. Hey, everyone. So my name is Peter Starfinger, and today I'm going to be presenting on digital forensics applied to containers with the idea that we're going to be enhancing intruder dilemma. Again, anything that you see today is definitely not reflective of my employer, anybody that I affiliate with. Really, what you're seeing today is just a result of my open research, what's openly available out there, and of course, some of the things that I have done kind of hands-on as a part of that research. This is a little bit about me. I think really just if I could sum up what's in front of you, I've spent a good bit of my time over the last 15 years just really trying to balance out everything from formal education to research to participating in my community. All this stuff is really important to me. Whether it's at my place of business and the people who trust me to take care of them, or even back in the community where I get a chance to, uh, you know, kind of represent my career choices and maybe encourage other people to think about the same sort of career choices. As far as the presentation today, again, this is kind of an overview of what the flow will look like. I'll try to talk about the differences between containers versus virtual machines. I know that gave me a little bit of trouble early on. I'll then talk about kind of at a high level what the IT environment looks like when you're employing a container technology. And I'm going with Docker since that's most commonly used. And then I'll talk about some of the security features that are inherent to Docker. And then, of course, kind of some options you have, whether you're coming from the administration side or even more importantly, as it relates to Docker, the development side. Um, and then I'll really dig into the meat and potatoes after that, which is really what analytical opportunities are afforded to us as a result of the choices that were made on how Docker is meant to function. And then finally, towards the end, I'll point towards some open resources that I found to be helpful. And that'll just kind of be a range of everything from tools, the methodologies to, again, things you'd probably want to follow up on if you were interested in applying digital forensics to a Docker environment or generally a containerized environment. And then at the very end, before we get to the Q&A, I will tell you about future talks that I'm planning, which I hope you'll all attend as well. So here we go. All right, well, just kind of splitting a hair here, and I don't even want to call it a hair. It's actually a big difference. When we think about virtualization versus containers, we can kind of see on the left that I've kind of shown the different kinds of virtualization. And from a virtualization point of view, there's a type 1 and a type 2 virtualization. Type 1, just to kind of point to a vendor as an example, would be like VMware's offering ESX. And the idea is that pretty much you have bare metal, and then you have your operating system with the hypervisor, and then, of course, there are virtual machines running on top of that. Another version, again, type 2 would be something like, again, at home, if you ran something like VMware Workstation, and that would actually be your hypervisor. And, of course, you'd be running any machines that you like. Now, what's important about any kind of virtualized environment is that when we start virtualizing, we actually start hard committing hardware resources from our host, and so we're dedicating so much disk space, possibly entire disks. We're dedicating sections of memory. We're dedicating maybe some of our processing power, potentially entire cores, to our virtual machines. And this is really where containerization ends up being different. From a containerization perspective, when it comes to the hardware side of the house, most of everything is really kind of running inside user space as a rule of thumb. And when it comes to hardware, really all hardware is kind of a shared resource. And when it comes to the containerization side of the house, really what you start to zero in on when you're using containerization is maybe limiting the amount of resources that can actually be used by your container rather than pre-stating the total amount of resources that must absolutely be allocated. Again, if I were to think about this in terms of a metaphor, virtualization is like carving up a pie, versus containerization is more like everybody has a spoon and there's a pie. Okay, and I'm just going to kind of jump to the next slide. There is kind of some interesting stuff here as far as the containerization column, and so I want to zero in on that in the next slide. And so here's kind of what the Docker environment looks like. And effectively, there's typically, the Docker client. And when I say Docker client, just to really relate that to us, there's actually an executable or a binary that you would be able to run called Docker. And then there's a series of different commands you can execute. In this example, we're showing the use of Docker, with build as a command. And typically there's switches that we can add to that if we're going to build an image as an example, or if we wanted to, again, use our Docker tool to take our image that we've built from our code or our manifest, and we want to store it inside of a registry, we might use the push command. And I think the bottom line for our purpose right now is just that, there's something called the Docker client. The Docker client is just really a binary you would run in order to interact with the Docker engine. Docker Engine is interesting because Docker Engine absolutely consists, of a daemon running in memory, almost like an API. And whenever we're using our Docker client to give instruction to the Docker Engine, again, we're just hitting that API and we're asking it to load typically images that are stored locally into memory. And when the image is loaded into memory, typically we call that a container. And so there's a bit of a life cycle sequence there where, again, we're absolutely storing everything that's necessary for a container to exist inside one of these images. But again, when we run our images, that's when we start using the word container. There's also such a thing known as a DockerFile that's real critical. And really, I was using the term earlier, this is really your manifest or your infrastructure as code. This could be stored wherever the client is being run from, so we can actually build from our infrastructure as code and make our own little personalized images that we later want to run as containers. Or it could even be, in a code repo or a VCS to be a little more specific, version control system. And then again, just pointing back to it, when we don't have our images local, and again, there could be some complexity. As an example, a developer might run all these things locally versus maybe in a formal IT environment. These may actually exist in their own dedicated systems, and this Docker daemon may actually have an exposed API that you can interface with over TCP/IP. And still, again, execute the same instructions using, again, your Docker binary, but now rather we would be invoking that, over a network. And when it comes from a registry point of view, registry is typically where we're storing all of our images that we have built from our infrastructure as code, which is the DockerFile. And on the systems that will actually run our images, again, typically you have to instruct that image to be pulled down from the registry to the system that has the Docker engine. And then after, again, the image files have been downloaded, now the Docker engine is actually able to execute and turn that image into the running container. All right. Well, when it comes to the Docker daemon itself, there are kind of some key security features I'd like to point to, and we're not going to really dig at these really deep, but I think conceptually it's just important to get this. What's interesting about containers and kind of where the security aspect really comes into the use of containerization is that, when we are again running our images and they're becoming containers. The minute the image is loaded into memory and it's assume that new identity as a container, it's running in its own namespace. And what that really means for our purpose is that there is a uh, dedicated um, um, virtual system from a memory standpoint. Uh, and from a container point of view, it believes that it's its own running system. It doesn't see the host. It actually thinks that it is the host, and it's just running whatever binary or code that you've put on it with again a dedicated OS. But the truth underneath the sheets is that from a Docker engine point of view, what we really have again is this thing called a dedicated namespace, and the namespace consists of things like a virtualized mount point. We have virtualized PIDs. As I mentioned earlier, if you were inside one of your containers and looking at memory, again, you would not see the actual kernel that's running on the host. You wouldn't see the Docker engine that started you. You would just see that again, memory looks like whatever it is that makes you real in memory. Again, IPC, any of our network layer stuff, all those things are going to appear as being slowly owned by, again, that running container. Some other things that Docker kind of manages for us, in addition to namespace, is something known as control groups or C groups. An example of that is the runtime environment run C. Run C is something, and I'm gonna say this badly, but there is a group. It's the open container. Oh, I knew I'd say their name badly, but anywho, I believe it's OCI, and this group created Run C, which again represents a runtime environment for running container images. And so effectively, this runtime environment is doing something called a control group. And a control group allows us to, again, further virtualize, if you will, what limitations we're going to place on the amount of hardware that can be consumed by a container. And that pairs really strongly with the namespace, because now we can say things like, yeah, absolutely, you have your own dedicated memory structure. You have your own dedicated network. You have your own, dedicated Unix time sharing system, which is like, as an example, the host name you identify by. Absolutely, all that's dedicated to you. But by the way, you only have 2 gigs of memory, as an example. And so C groups really allow us to kind of button up, if you will, how the file system and all that really presents to the container, and what it can really access, and the limits to that, if you will. Kind of moving along here. And so kind of in addition to that, so we have namespaces and control groups. Those are, again, managed by the Docker engine, and the way that those are utilized are certainly defined by how we leverage our client, and how we define our containers when our images when we do want to run them and they become containers. But kind of in addition to that, we also have other features that the makers of Docker have added that allow you to instrument additional security. As an example would be SE Linux, and SE Linux is something that you can use in combination with Docker. And I think what's important from an SE Linux point of view is that, unlike the discretionary access control that is kind of baked in with the Linux file systems, where everything is owner group, everyone based. Now you also get into adding security labels. And so again, if a process, even though it might be run under a certain user context, may grant it exceptional permissions from a file system perspective, or even a memory perspective, if the labels don't exactly match up, now we can restrain what it is that a particular container is able to do on a host, from, again, either a memory or a file system perspective. And some of the ways that that's realized, and this is a little operating system relevant. So, as an example, if you're running like Red Hat or CentOS, there's already a default policy for Docker. If you do have SE Linux and Docker on top of one of those operating systems. Um, for some of the other Linux variants, there are additional kind of steps you may have to go through, which are, in my opinion, seem to be pretty well documented, um, on the Docker website itself. And so they call this kind of this default protection mode from an SE Linux point of view. They call that a targeted policy, and that's where, again, the people who make Red Hat and CentOS have already taken the time to kind of figure out from a labeling point of view what you really need to access when it comes to running, any container on a host. There's also such a thing called unconfined mode, and again, you can put this in your infrastructure's code or your manifest, the Docker file we're talking about earlier, where we could say that, hey, you know what, labels don't matter, give it access to everything. Now, that's a little crazy if you went so far to have SE Linux already involved, but you can totally do that. They call that unconfined, and there's also something called MCS, and that's where you take the time, and this, it really helps if this is the developer doing this, but where the developer takes the time to create the appropriate security label. And so the kind of libraries and different accesses that the application needs to function is allowed correctly, rather than, again, let's say you're more on the IT administration side, instead of you trying to discover that for the application. Okay, just kind of moving along. Of course, you can also invoke App Armor. I'm sure a lot of you have practice with that, and that's really where we're just kind of restricting on that container, what folders and binaries, our container to be able to access from a host perspective. Kind of additionally, there's also seccomp and seccomp. Again, it helps if the developer is including this in their manifest. Effectively, you just define like what syscalls you actually want that container to be able to make. And again, if we can just imagine these three things, SE Linux, App Armor, seccomp, all kind of being used in parallel, you can really add a lot more strength to your application being able to function as you expect, but without really putting the host so much at risk by having a free-for-all situation. And if I'm just speaking just really plainly here, if you're a dev and you're just again trying to get your infrastructure's code right and running kind of a localized environment, it's definitely good to define this stuff up front. Maybe it doesn't feel as important, but I think when we start moving into our CI/CD kind of environments, I think that's really why you want to spend the time to do this. You're just going to help all the ops people and security people later down the pipeline, who are dependent on how it is you create the security around your application. And then just kind of building on that, some other security we can add. And so I know I spent all this time talking about how virtualization is different than containerization, but you can invoke the hypervisor just to give you an added layer of security. And if I just had to make this as simple as possible, again, imagine that you have a virtualized guest, which is going to have already limited resources, and then there's a true host, right? Maybe it's a type 1 operating system, but there's to then have some control if something were to happen to the guest. And now we can kind of bring to the table some of our just known security practices when it comes down to the hypervisor. Some other options we have, and this is just more kind of image specific or container specific. It really comes down to our use of IP tables and or UFW. Really, we just want to make sure that if we are running more of an enterprise type environment, that we do something that isn't necessarily baked into Docker is security mechanisms around the interface. And so you kind of have to add using something like, as an example, mutual authentication through TLS or maybe even SSH. You kind of have to add or bundle in, if you will, the AAA services, if you will, to kind of protect that API. A lot of the abuse scenarios that I think were, I don't know if this is so relevant now, but early on, a lot of the abuse scenarios were is that people were network exposing, their Docker API, and pretty much, if you see that port open, you can kind of get to work, and so that's a great opportunity, or something else that you can do in mass. Again, if you're scanning out there for open Docker APIs. And then finally, just here towards the end, the no the privileged option. If you don't use that with your container, really what that means is that we're going to allow that container, that image, to be loaded into memory as a container without using root level privileges, and that's really useful. I'm not sure the exact circumstances why you would want to run with the privilege switch. But with that being said, the Docker client does offer you plenty of opportunity to do some pretty crazy stuff. And so don't use privileged. That's it. And then rootless. Rootless is an option. Again, I think use a whoever the developer is, probably needs to be a little more mature. If you're going to go rootless, you don't need to mount the root operating system or to run your container. And I think some of the prior controls with SE Linux, AppArmor, SecComp, I think all those provide us a lot of coverage. But again, if you can go rootless, now all of a sudden we're really shifting, where root is, and you could probably move that into a directory of no consequence. And now really what you're dependent on, again, is just making sure that you make the right libraries available, to your container, which is absolutely possible. I think it does take a little more effort though to become rootless. Okay, well, let's kind of get to the point. So, look, at the end of the day, when we're doing forensic analysis, you can kind of see, again, that process you would go through, and this is well documented with Nest. This is kind of the process that we might go through in order to perform analyses, and some of the expected outcomes is that we are trying to understand when there is an environment compromise, how far did potentially that third party get, and what kind of tactics, techniques, procedures were invoked, by that third party. And of course, there's, if we're able to get to that point, right, we're able to inflict, what everyone's just kind of recognizing, a lot of pain on these third parties, because now we predictably know how it is you operate. And again, those are all advantages of forensics. And the way everything we just looked at relates to that is, these security mechanisms exist, and their usage should absolutely affect how it is we try and understand how a compromise of an environment may have occurred. The lack of their usage or their insecure configuration is absolutely what creates opportunity for the environment to be compromised. And so, as a forensic analyst, it is possible, by just simply discovering, that a security control is missing, that might quickly lead you to also how an environment may have been compromised, and therefore creating some pretty low-hanging fruit that you could pass back to the devs or the administrators or engineers that were involved in the particular IT environment that you're trying to help out because it's been compromised. Okay, let's get to some stuff that looks like maybe you could walk away from this presentation and get some work done. So again, we're going to tackle those system components, and those were kind of those big swim lanes, those columns where I had the Docker client broken out, the Docker engine, and the registry. I'm just going to kind of comment on what it is you might find there. And then we're also going to look at kind of the individualized components, if you will, that allow us to get to the point where we actually have something running in memory that we might be concerned about. All right. Well, let's start off with again, these are just kind of natural artifacts that are going to be created from the life cycle of again those system components existing. When it comes to the Docker engine itself, what I ended up finding was that all of our runtime configuration, if you look underneath init, you can find as an example where the log file is configured to sit at, as well as some of the other preamble stuff that's used by the Docker engine before it ever starts up on a machine. And so this is a great place to look initially. Some other places that we might want to check is the actual runtime as it was. We can see things like the PID that the Docker engine was running under, as well as many other things as it relates to the runtime environment from the machine that you might have access to. Other areas we might look, we may want to find out what version of Docker engine is being run. There seems to be this consistent relationship between vulnerabilities existing, as an example, on the operating system side, and then those being fixed, and that creating a downstream impact on the Docker engine itself, which then has to be fixed. And so there's kind of this whole thing around this interdependency between the operating system, its flaws, and of course, again, their repair affecting the Docker engine itself. And so, getting that Docker engine number really allows us to do, what we're good at. You kind of crawl some of the open vulnerability databases and just say, okay, it's this version. What do we? I think that kind of gives us some clues. Some other things that we can look at too, again, is the actual Docker root itself. What I've seen with the installs that I looked at was that everything seems to be underneath. And underneath this Docker folder, this is a folder, we end up finding everything from our images that have been downloaded to the machine to containers that have ran. And you really just kind of have, I mean, as a forensic analyst, I mean, this is where you're really going to be able to find a lot of your truth, especially when we know there may be malicious maybe containers that end up executing in the environment. And then just kind of digging, really I'm just digging into that varlib folder. And the only thing I'm saying is that if you want to see all the images that have been downloaded, there is a repository.json. You can use a tool like JQ or something like that to look at that JSON and make it a little more readable. Or again, if you're more comfortable with Python or something, again, just import your favorite library and just recognize here's this nice JSON file where we can dig and kind of learn about what images are on the machine. Something else that's interesting that we want to care about as forensic analysts, and this is italicized right here, but effectively what's going on is that there are some different file system options as far as how those images are stored. And so you definitely want to look and just kind of see, underneath, this image subfolder within the Docker root, what storage drivers are popping up. And then you can kind of pair that with, one, your tooling, and then two, what documentation you're grabbing from the Docker side of the house if you want to understand a little bit better, how those images are actually rolled and used. And also this would, in addition to that, kind of dictate that if you don't have the appropriate driver, it's going to be hard to work with that image later if you want poke at it in the way maybe a user would see it. And again, in addition to maybe some of your traditional forensic tools that I say traditional, there's also some new forensic tools we're going to talk about that will kind of help with this. But again, storage driver, definitely use that. And, if you're not familiar with whatever file system is being invoked or what storage driver is being used, again, the Docker website has that very well documented, and you could do a lot of this work by hand, especially if you didn't have tools to really help you. Again, use their documentation. And then building on that, we also have our image location. And so really our repository kind of tells us what images are there. And then our image location, there's something called ImageDB. And inside ImageDB, we have a listing of different SHA-256s. Again, those are all the images that have been pulled down to the machine. We'll comment a little bit more on that later. Then we also have our image layers. And again, the layers are effectively what our images are comprised of. Um, and you can see again, this is going to be right underneath of our Docker root. And then right underneath Docker root, notice how we're not actually in the image folder. We're directly into the storage driver that we found earlier. And now we can start to look at, again, what the different layers are that make up a particular image. And this is real important, when the operating system, again, wants to load an image into memory. And as we just kind of go down, the list here, we also have, the containers that have run on the system. I think a lot of you are probably familiar with, like if you do like Docker PS you can see all images that have ever executed. And the way that Docker is able to tell you all that is because it's storing every time it can. So even if it exits, my experience so far has been that this stuff is still sitting out there. And so we can kind of go back, just like if you're running Docker PS from a forensicator point of view, if we've got a full disk image, we can go back and go look and see what's all run on that particular node. And then just kind of moving down the list here, again, I just keep pointing back to that storage driver. That's so key to being able to, look inside these containers, especially if, again, post-mortem, you need to do a differential analysis to see, what's going on in a container versus the original image that it was loaded from. Again, could be a circumstance where, what really went on is that, the running container itself was vulnerable and it got popped, and there was some badware that loaded on it. And that is the whole reason why you're there serving and trying to understand what's going wrong. Really, there isn't a bad image. There's just a compromised container. Hopefully you follow my meaning. And then just kind of going down the list, the other thing we kind of want to look for, and again, it's possible, it could be an incident where, maybe this is some kind of a development server. And again, somebody took the liberty to go ahead and just IP enable the API. And as I was talking about earlier, if you don't, bake in some security around that API and it's just wide open. And by the way, we put it on the internet and made mistakes like that, or maybe somebody got on the inside of the environment. And now they were trying to do some lateral movement. And the first thing they find is, here's all these APIs that are wide open. The bottom line is that if there is a network enabled API, there are some locations that you can check real quick to see if it actually is network enabled and not just the Docker engine is not just accessible locally from the host, but actually, from the network. And so I list out those locations that you can kind of look at and see what's going on. Something else that's kind of noteworthy, before I get off this page, is the registry itself. If there is a local registry, and that is, again, it depends on the maturity and the environment, right? If you're dealing with a really immature environment, or if it's a development machine, again, just take a look underneath varlib, and if somebody decided to run a local registry, again, you're going to find your image stored there. And I think what's really key there is not only do we have some options I'll talk about later as far as forensicating, the images themselves to understand what happened over their history and all of that. But I think more importantly, if it's sitting there locally, I feel like the bar is significantly lowered for somebody to do malicious modification of potentially a legitimate image that's being used in the environment. Okay, we're going to keep going here. Quick time check. Okay. So from a Docker engine point of view, it's also possible, this isn't guaranteed, again, it depends on how mature the shop is, but you can configure logging in the firewall if you are turning up those APIs to be network exposed. And again, it depends, which, if you're using UFW or if you're just using IP tables, again, that kind of dictates where some of those messages might land. From my point of view, I just feel that it's just convenient to kind of say that, hey, if you do find that Docker was configured, to have its API network accessible. Again, just take a look and see if we have a messages log file. Just peek in there and see if we've already configured logging in the environment. If so, great resource. We can probably tell part of the story, especially if we're coming in to the work with IOCs in hand already. Indicators of compromise. Additionally, again, if there's a UFW, and that would totally make sense. Again, if we've invoked logging, we're going to find it here. It's still again inside of var log. And if the specific logging is not set up within UFW, I think the default location is this kern.log. I think the bottom line, as a forensicator, again, if you've got a network IOC going into the work, just go ahead and go underneath var log and just do a quick search and see if you pop anything interesting. Just kind of moving down the list, when it comes to Docker client, if you get a developer machine that was suspected compromised, or again, you see, that Docker client is on a machine that was handed to you, it's possible that the Docker client is on a node that may have been provided to you. Go ahead and queue up your raw searches, your index searches, whatever it is you might have. As an example, if you're hitting memory, maybe it's bulk extractor. Go ahead and put these terms in there, because these terms themselves can definitely be indicative of if you have hits. They're worth exploring further to see if we do have any malfeasance that's associated with whatever was put after that command. Again, each one of these is representative of a different invocation that we might make from the Docker client itself. And then in addition to kind of our keyword searches, I'm just really trying to scope those so you can more quickly get results. Again, checking unallocated space, specifically, slack space, swap on your disk. That might yield, some results. And again, this is all kind of in addition to memory. Again, in memory, not only do we want to check, any of the allocated frames, but we also want to go ahead and just check free space and see if we have anything pop out there. Again, using those terms. And finally, again, if you're on top of a developer station that there's very suspicion about, or again, if you're seeing that, that Docker client there, go ahead and check, the shell history files, check the Vim history files, and just see, again, if these terms have hits there. And if so, see if you can start to kind of stitch together a picture on what might have been wrong, within that environment. And, and I do kind of want to say, if we are talking through a lot of different kind of ideas on where it is you may find electronic evidence. It is possible that, again, the situation you might be facing could still be as simple as there was a vulnerability in the running container, and that's what was. Nobody ever got any further than that. With that being said, what I'm sharing with you is absolutely just taking advantage of the fact that there's a specific way that you have to use, that Docker client binary, and because of that, that does give us a great starting point, especially if we're looking for abuse scenarios, which again could be one of our developers' identity being hijacked because of a drive-by, and then some operator wakes up to the keyboard, and all of a sudden they decide to get to work. And just kind of moving down, again, infrastructure as code. When it comes to those Docker files, again, they have to start with, Docker file in the header. And because of that, if we're going to be doing some file carving, if we think that, some weaponization was done in the environment, go ahead and make sure DockerFile is in your list of file headers that you carve for, and, get to work. Go ahead and work unallocated space. Definitely check, the actual files that are available. And again, if you have any hits on DockerFile, you definitely want to take a look at those and just kind of see what those manifests say. That may give you some significant clues itself, in addition to, the images or containers that you might find on that machine. And then, of course, I'm just pointing back to, again, looking at, history file. If we again have somebody who is able to maybe establish foothold on a host, or maybe hijack some developer credentials, or maybe uh, you know the everything is all in one on the node, and here it is, we've got root access from one of the containers because of an insecure configuration. Again, take the time, look at those user profiles. If you end up finding Docker files, you probably then want to go a little bit further and say, okay, well, what edits do I have on these files that are recorded? And you could probably discover some of the process the third party may have went through to continue maybe exploitation of your internal environment. Um, and other things to kind of look for, of course, look for things like, if we're this far and you can clearly see that there's some bad files that are these manifest files are existing, you probably just want to go ahead and just take the time to see if pull curls or something else that may have been executed on that machine. Just again, checking your history files for those. I think that'll kind of help you tell the story if you're starting to get into a more extreme scenario where maybe you do have a compromised node, which is a much bigger deal than just simply having a vulnerable container that may have been abused. And then just to kind of comment on the Docker file itself, let's say we do discover these. Again, you should clearly see Docker file at the very beginning of the file. That's really what I mean by file header if you aren't following that language. And then, closely thereafter, we're going to find, all the things that make potentially an image become real, short of running the Docker build, which would actually, create that image. And it's everything and typically because we're talking earlier about layers, right? Typically, when we're making a container, a lot of developers start from an existing image. It's possible that say, hey, that's where I want to start off at, or maybe it's Ubuntu, or maybe Python in my runtime, and so there's existing containers that Docker's open registry would allow you to reuse, and so you would see that instantiated in the from, and then copy is a section in the manifest where you would actually find that if there were libraries, as an example, that somebody staged, or binaries that somebody staged on the host that they wanted to include inside the image, you would see those referenced within the copy command. And so that's a big clue of maybe additional files or directories that you might want to go take a look at and see what else may have been staged there in order to make that image or container that you're concerned about in the environment. Working directory, that's the directory that's going to be used runtime. Run command is, run is effectively, what is it when that image gets loaded into memory by the Docker engine. Now it's a container. What is it that it's going to invoke and execute first? And that's usually exposed by the run command. CMD is typically the entry point. So, just like, if we're doing like bin analysis, we have an entry point for our containers. And that's always, instantiated in the manifest by this CMD section. So definitely take a look at that. You might find everything from clues maybe on how a running container may have got exploited when it was running live because of the decisions that were made on the entry point, to maybe that's where the actual bad stuff is. And then finally, expose. Expose is what allows a dev to actually take a service and make it network accessible. And depending on how the expose is written, that will greatly affect, again, what might have been exploitable, depending on what it is we're talking about. Or maybe, if we're wondering, how the third party is able to, I don't know, instrument their backdoor, it could be through that expose command. Okay, great. So moving right along, when it comes to images themselves, something that's really useful is that, we definitely want to check, if we've got a copy in memory, let's go ahead and check memory and see if we can find maybe some exposed keys that were left laying around with, any whether it be a memory image or a disk image. Typically, if there's a registry that's not local, a lot of times those credentials, maybe it's stored as an environmental variable. It might be underneath, the hidden folder of Docker inside the user profile. Usually there's, again, a JSON file there. Eat that up real quick with JQ or something or Python, and just kind of take a look in there and see if we have keys. And if we do, again, it's important, that you just be sensitive to the environment you're working in. Is that a registry that if it is a registry we expect, what do those credentials allow us to do? And that kind of allows you to kind of go that step further, of understanding, is this a rogue registry? Is it your existing registry that now has bad images inside of it? You could start to kind of navigate, some of those answers by looking for this. Some other things that, again, we mentioned it earlier, if there is a local registry, again, the examples I've seen, var lib seems to be where that ends up living. And then, when it comes to images themselves, we mentioned this earlier. We're going to dig a little tiny bit into this, but definitely this is what I want you to go explore from a forensicator point of view, is that when it comes to image listings, again, we're going to see that inside this repositories .json. And I think what's really kind of key here is that anything we see in there, if those images are missing for any reason, but you as a forensicator find that it's supposed to be there, in my opinion, this is a great opportunity for us to, potentially even try and look for those images maybe in non-traditional locations. Maybe we have some deleted files potentially. Maybe we can go look around for, and again, because it is SHA-256, that is such a long string. That actually is a great IOC or keyword that we can reuse just to kind of see where stuff pops up at. And again, same thing with memory. Sometimes, file handles might live longer than the owner expected, who was running a process that invoked a file handle to a certain image. And so if we have a file handle that is exceeded maybe the lifetime of when a file is supposed to be on disk, it is possible that the content of that file still may be malingering in memory. And so just simply finding something within this repositories.json, in my opinion, especially if it's suspicious, it definitely gives us a great chance of maybe finding an image that we're concerned about. And then finally, the image locations themselves, what's really important about ImageDB is that in ImageDB, earlier we're talking about the Docker file. Okay, well, all that stuff in the Docker file, the entry points and, what binaries were loaded, and really just kind of the history of the image, that is located inside the ImageDB. And then from ImageDB is where we actually end up finding, where our file system, if you will, where the layers are that make up our image are supposed to be located. And so there is a lot of not only historical value and clues, especially if we're dealing with, do we actually have the malicious image still locally? Again, this is going to tell us a lot of that story that we need to know and understand. But then additionally, again, when we want to get to the binaries and libraries that may have been tucked into those layers, so the container is actually functional, again, this is where you're going to find that at. And the way you're going to know that you're looking at the right layers is based on, what we're finding inside the image database itself. All right. So just kind of moving along, again, when it comes to containers themselves, earlier, everything I've been sharing is totally just, I've made the leap that you've got access to disk memory. Somebody's handed you something and you're just supposed to kind of work with the evidence. If we're in a different situation where, our situation is that we're coming in, we're a little more on the incident response side, and the team, has just found that, hey, we got some bad stuff running on these machines, and we know that's part of the containerization environment that's being used by the company, and it, because of the advancement of endpoint detection response tools, or even a lot of the kind of the free and freemium type security that's out there. A lot of times, our first responders, they already know, process identifiers and network connections and things like that. And so if you're coming into the game, somebody's got a PID that they're concerned about on a specific machine, go ahead and dump that PID. Gcore is a great tool for doing that. I think if you're ready at that point where somebody's got a PID in hand that they're concerned about, just grab that right out of the gate. And then my opinion, here is go ahead and get a copy in memory. I think there's a lot of ways to instrument this. If you're well prepared for your environment, you've probably got Lime already built for what's running in your environment, and you just want to, again, go ahead and invoke hopefully some automated flow, get Lime out there, go ahead and get your copy in memory. And then finally, if we know that there's a container that's active in memory, again, we don't know the story yet. It is possible that that container got out there. Again, I was describing that whole situation where the container may just have a vulnerability that was abused. Go ahead and use Docker commit on that running container. And what that's going to do is the Docker commit, definitely check that out later. But Docker commit is going to allow us to actually take whatever file system changes were made to that container and make a new image from it. And so we're just going to drop that right to disk. And then after we've dropped that disk, a lot of, whether you're in a cloud environment or a virtualized environment, again, significant advantage if that's what your IT staff is using, go ahead and just snap them disks, because now we've got, our committed bad container that we're concerned about. We've got potentially our, assuming we didn't, move them to some other network location, we may have our memory capture and our process dump and everything just kind of sitting there for us. And now we can actually go out of band and kind of get right to work doing some of the stuff that was described earlier. And then here, as we get to step 5, step 5 is kind of assuming that step 1 through 4 has happened. We've grabbed all those nodes that we're concerned about that had the Docker engine. And now we just got to get to work. And really, here's just kind of a stepped process that I think works based on what I know right now. Let's just go ahead and identify, where are those rogue containers? And a lot of time, by the runtime arguments, we get a pretty big clue whether we need to care about a particular container. And then, again, just checking, for the actual processes, because at the end of the day, the container is just a process in memory. Let's just go ahead and dig and see, what some of the actual libraries that are loaded around that process, and see what kind of handles have been invoked. It's possible that, somebody may have gotten on there and maybe had a little, again, not a rootless access, but full root access. And now they're just busy doing all kinds of bad stuff on our host. And so we'd be able to spot a lot of that by just kind of digging at, what handles are there and what libraries have been loaded with that process. Then also, network connections. Again, typically what brings us, to a machine, 9 times out of 10 is that our incident responders, they're going to give us, network IOCs to start with. And so we can, again, use those when we're out there, doing our memory forensicating. And then finally, environmental variables. It is possible that there's bad that's stuffed up into the environmental variables. That might have been initially from the image, as we described earlier. You have those run and those entry commands and all that. But then, and again, in the live environment itself, if we have some kind of abuse, a lot of times this just seems to be the place to hide things that maybe a third party or even your own developers might think are secrets. Once it's an environmental variable, that means it's in the clear to us. So might as well look. And then finally, just to kind of wrap this up, when it comes to analyzing these containers, use all that work we just did on the memory side to look at the disk side. And, we know where our containers are. Again, they're right there on the disk for us. And so we can kind of start to kind of pair these things and figure out if our truth is, do we have a full environment compromise? Or again, do we have an internet drive-by because maybe an administrator was careless and didn't protect an API, or something simple like that, rather than the worst case scenario, which is, there's a different level of compromise in your environment and somebody's actually been able to get the host, or maybe somebody laterally moved to the machine, again, we'll be able to start to kind of differentiate those things as we start to look at that difference between what we found in memory versus what's on the disk itself. All right, and there's a lot of other steps here, and I'm just pointing to what's kind of traditionally accepted, right? Again, if we've got disk and memory, let's make sure we're using hardware write blockers if possible, and then some kind of software write blocking if we're mounting images, mounting disks, mounting volumes, things like that. And of course, we do want to go ahead and check all of our container logs. In these locations where the containers are. There's great logging kept while that container is up running. And again, the layers, we just want to make sure that we're mounting those read only in addition to maybe the disk that we've also mounted with our write blocking read only type permission. And again, timelining tools against the artifacts that are on disk, we can't just throw timelining out the window. I think all that previous stuff we know to do as forensicators when it comes to file system analysis specifically. Again, that needs to be in play right now. And then we augment those other timeline type elements that we would get from the containers and images and everything else with those traditional timelines that we would end up getting from file system forensics. And then of course, diffing the container compared to the image. Again, we're going to be able to look at that container and see what its original image was. And if that's local, we can start to kind of do that comparative analysis, which would be comparable to running something like a docker diff command. Oh, and bonus, since we have that disk image, we can always turn it back up live and in a more contained, controlled environment. Again, use those traditional Docker tools to go about our analysis. And I'll mention some more of that here in just a second. Okay, just kind of moving along. So what options do we have as analysts? Look, to me, I think when it comes to free, between Gcore and Lime, I think you're ready to go. Just make sure for any environment, if you already know what images are going to be used by the company to run the hosts themselves, if you already know what operating systems are going to be run, please take the time to go ahead and just have your Lime artifacts built in advance. This way you can just kind of get straight to work when it comes time to collect a memory image. If you do have the convenience of snapping memory or sleeping the running asset and getting a full physical, then that's great. I have a feeling though that sometimes that's hard in most situations. And I know with a lot of the cloud providers that could be, really hardware specific that the actual image that is the host is running on itself. So anywho, just make sure you have some memory acquisition tool ready. Make sure you get memory. And then kind of in addition to that, when it comes to, disk and container, collection, when it comes to containers, we mentioned that Docker commit. You also have something called Docker export. And that really allows us to take an image and put it into a tarball. So if you get in a situation where maybe it's not there's not a big gig network backbone that's supporting the environment, it's tough to move around a high volume of data, and you got to put people on ground to go, go get those disk images for you. Again, this export command may save you a couple steps and allow you to at least get the file system from that Docker commit command that you ran, and just get you some kind of interim artifacts, if you will, that you can work from. And of course, native utilities. I feel like I've been harping on that the whole time. If it's whether it's a VMware based environment or if it's GCP, AWS, Azure, tons of options to snap disks, take advantage of it. And of course, if we cannot do that, we can always drop our acquisition tools directly on the running device. I think this is a worst case scenario and really risky and destructive. But if you had to, you could totally go with your bitstream tools onto the victim asset. I'm not a big fan of that. And then when it comes to image analysis itself, again, just remember the terminology. Image and container are different. Images, again, actual package that we might want to run as a container. And so there's some great tools out there for that. By the way, shout out to the DevSecOps group. I actually picked these up from them. Whale or Dive, these are fantastic image analysis tools. And I'm not removing your responsibility as an analyst to, go look at the storage driver and understand how it works and be able to work that by hand. But with that being said, these are some great tools that'll help you, especially if you've already got your hands on a disk. And then finally, of course, the Docker commands. If you have to, if you got a copy of a system, that means you could probably turn around and spin it up live if you needed to. And so you can still use Docker inspect and Docker diff to figure out, what was going on with a particular, image. If you expect, either a malicious image or some kind of image compromise going on in the environment. And then for container analysis itself, I think Docker Explorer is a great tool. Please check that out. You can see the authorship there. It's a pretty big company who's standing behind that. And then, of course, there's also the Docker Forensic Toolkit. I've gotten great mileage out of both of these. Some recommended reading. If you haven't looked at NIST 800-190, please do. I think this is really handy for forensicators to understand. The security aspects of this stuff. It 100% complements what we can do on whether it's the dead or live analysis side. And then also the sysdig people, please check out sysdig. I think they've got some great open source tools, but they have something called they took the attack model. And every bit of research I did on the pen testing side of the house for Docker, these guys have already put it inside MITRE ATT&CK. So just go look at that, and I think it's a great resource to measure what's your not only your capability to detect attacks, but I think as a forensicator, if we're trying to fill out, what happened in that kill chain and we want to get all the TTP, well, they've listed out all the TTP against specifically Docker. And then finally, our traditional tools, we definitely want to make sure that, we're leveraging, TSK and SleuthKit and recall and volatility. There's a lot of great traditional forensic tools. And if we just go back to, what we learned earlier in the very, very beginning, which is that, whenever we run an image and it's loaded in the container that is running in user land space, and everything as far as parent processes are concerned, that's going to be that Docker daemon, that Docker engine. The Docker engine is going to be bringing, that container into memory. And so you will have a specific process ID that's associated with every PID. And so all that stuff that's highly documented out there in volatility and recall projects, you could totally apply that in order to dig into, those running containers when you have concern about them. As far as next talks, I realize we're a little further along right now. But as far as next talks, again, if you guys enjoyed this, I'd love to come back and talk about, analysis of malicious containers. I'd love to talk to you about, Kubernetes forensics. I've been putting a lot of energy into that. And then kind of leaping from Kubernetes, I'd love to jump into, SaaS offerings of that, at least of the major cloud providers, and just talk about what some of your options are there. And again, kind of a similar approach, what are kind of the security things that may exist out there, and then how do we consider that as we're going through our analysis to figure out what may have went wrong. And then finally, much bigger picture, CI/CD forensics. I'd love to tie back to, if we get past, if we get to the stage where we're like, oh no, it wasn't just a vulnerability in the container that was abused, but rather somebody broke out of that container and now they're in our environment. I'd like to address that from a CI/CD perspective, maybe some considerations you might make. Obviously, that's not the full picture if we have a group doing lateral movement, but I feel like talking about the CI/CD environment, there are just a great volume of forensic artifacts that are worth exploring, and totally related to whether we're talking about cloud or containerization as an idea, or even virtualization. And that's it. Does anyone have any questions at this point that we want on the recording? If not, I'm going to ask that we stop the recording. Anybody want to raise any questions now? Okay, fantastic. Yeah, if we could stop the recording, that'd be great.